Sonar arrays deployed along the continental margin had been designed for long-term monitoring of abyssal currents, seismic microevents, and deep ocean acoustic anomalies associated with shifting tectonic boundaries. These arrays, anchored thousands of meters below the surface, operated continuously for years, recording the slow mechanical breathing of the Earth's crust, the constant rumble of distant submarine landslides, and the faint, mournful calls of deep-diving marine mammals migrating through trenches older than human history. Most of the data consisted of low-frequency noise, predictable and monotonous. But then, during a period of unusual calm in the ocean's acoustic environment, the arrays detected something that did not match any known geological, biological, or mechanical source. It began as a faint tapping pattern barely above the noise threshold. The pattern appeared as a series of evenly spaced impulses separated by intervals too regular to be random. Sonar analysts initially assumed it was interference from equipment or an artifact of distant shipping traffic refracted through thermal layers. But the impulses repeated at exact intervals, unaffected by tidal cycles, current shifts, or surface storms. The knocking came from a location several kilometers below the seabed of a trench known for its extreme depth, where pressure reached values no instrument could withstand, and where geological processes operated on timescales longer than civilizations. The rhythmic knocking persisted for days. It did not drift in frequency. It did not fade with time. Each sequence of knocks maintained perfect temporal consistency, separated by gaps so stable they formed a near-perfect clock. Something in the abyss was producing pulses as precise as engineered machinery. Yet no known machine could exist at those depths. The sonar analysts isolated the signal from background noise and mapped its propagation. The impulses originated far deeper than the trench's documented maximum depth, coming from a region where the water column merged with compacted layers of crustal rock and descending tectonic slabs. No cavity large enough to sustain acoustic energy existed in that region according to conventional geological models. When more arrays detected the same knocking, triangulation revealed that the source was not spatially static. It occupied a region beneath the trench but shifted slightly across days, not in the manner of a drifting object, but like a resonant source migrating within a layered geological structure. The shifts aligned with subtle changes in seismic strain detected along the subduction interface. This implied that the knocking propagated not through water, but through rock, using the lithosphere itself as a transmission medium. The pattern intensified after a minor seismic event in the trench. Following the tremor, the knocking grew louder, as if the disturbance had cleared some barrier or opened new pathways for acoustic transmission. The impulses doubled in amplitude and became detectable across a wider portion of the monitoring array. The interval between knocks remained constant, yet the spectral shape evolved, gaining overtones reminiscent of harmonic resonance within confined cavities. But no known cavity existed at that depth. The region was heavily compressed rock, fractured only at microscopic scales. The spectral signature suggested something interacting with the internal stresses of the crust itself. Over subsequent weeks, researchers analyzing the signal noticed a remarkable property. The knocking displayed frequency-dependent attenuation corresponding to the boundaries of geological strata. As the source shifted deeper, the higher frequency components vanished, leaving only low-frequency impulses that still retained rhythmic precision. As it shifted upward, the harmonics returned as though the source were embedding itself into different density layers, each amplifying specific parts of the signal. Patterns emerged, showing that the impulses matched the natural resonant modes of the subduction zone modes that took centuries to change. Yet the source adapted dynamically, maintaining its rhythmic timing even as the spectral shape modulated. Some analysts propose that the knocking might represent a form of lithospheric oscillation triggered by deep tectonic interactions, a natural seismic clock manifesting as repeated microfracturing. But the precision of the intervals contradicted this. Natural fractures do not occur at perfectly stable intervals for weeks without drift. The signal's coherence suggested a regulating mechanism, something capable of maintaining temporal stability despite chaotic geological forces. Attempts to model the signal using known physical processes failed. No earthquake precursor, no mantle surge, no basaltic resonance-produced patterns remotely similar. The knocking did not match any recorded seismic phenomenon in the global database. It was too deliberate, too steady, too controlled. Deeper analysis revealed that the intervals between knocks exhibited slight microvariations that coincided with fluctuations in Earth's rotational microtides, minute changes in gravitational forces caused by the positions of the Moon and Sunday. This meant the source was sensitive to gravitational fluctuations. That sensitivity would be impossible for any ordinary mechanical system buried beneath kilometers of rock. But the pattern held. When gravitational microtides increased pressure along the trench, the timing between knocks shortened by fractions of milliseconds. When the microtides relaxed, the intervals lengthened. These variations were so small that only the most sensitive equipment could detect them. Mapping these variations produced a deeper insight. The knocking appeared to anticipate microtide shifts, adjusting its timing slightly before measurable gravitational changes occurred. This predictive behavior defied conventional explanation. No physical process was known that could detect incoming gravitational variations at such fine temporal resolution. The pattern indicated not reaction, but synchronization. Something beneath the abyss was harmonizing itself with the rhythms of the planet. Months passed, and the knocking expanded into longer sequences. Instead of a simple repetition, the impulses formed composite patterns, cycles of high and low amplitude, separated by multi-day intervals. These cycles, when analyzed mathematically, revealed structures analogous to resonance cascades found in nonlinear systems. Each cascade appeared to encode the properties of the geological environment: pressure, density, temperature gradients. The knocking was not merely a signal, it was a reflection of its surroundings, a dynamic imprint of the trench's internal mechanics. Some researchers speculated that the knocking was an emergent resonance phenomenon, an interplay between supercritical fluids within the trench, mineral structures capable of storing mechanical energy, and the acoustic properties of the crust. But none of these processes could account for the temporal precision. Emergent systems typically drift. This did not drift. Others proposed that the knocking represented a geological heartbeat, the rhythmic contraction of subsurface structures as they adjusted to shifting tectonic pressures. But geological heartbeats, if they existed, would not produce such stability across months. As time passed, the knocking began to recede deeper, descending beneath the detection threshold of shallow arrays but remaining audible to the deepest sensors. The descent followed a predictable pattern. The source moved downward in correlation with subtle seismic relaxation events. This suggested that the knocking had entered a geological phase transition zone where pressure gradients and mineral phases changed rapidly with depth. The signal weakened but did not vanish. Instead, it evolved into a series of ultra-low frequency pulses that propagated through the crust like seismic whispers. Then, during a period of anomalously low oceanic noise, the knocking briefly intensified one last time. In this final surge, the impulses displayed a new spectral structure, extremely high-frequency components superimposed on the familiar low-frequency base. These high-frequency components lasted only seconds, but carried an unmistakable pattern. They formed a repeating cluster that matched, with uncanny similarity, the overtones present in the rhythmic breathing discovered inside the recovered capsule from another trench decades earlier. The correlation was mathematically improbable. The trenches were separated by thousands of kilometers, the events decades apart. Yet the patterns shared harmonic signatures that suggested a common mechanism, not a biological source, not a mechanical device, but an emergent interaction between deep ocean geology, pressure-induced mineral metamorphosis, and resonance forms sustained across extreme timescales. After this convergence, the knocking diminished slowly. Day by day, its amplitude faded, the intervals stretched, the harmonics disintegrated. Finally, After nearly a year of continuous activity, the impulses dissipated entirely. The abyss returned to silence. Weeks of monitoring confirmed total cessation. No further rhythmic knocking emerged from the trench. The resonance patterns vanished. The geological strata returned to their natural noise levels, shaped only by the slow grinding of tectonic plates. But when researchers conducted a final analysis of the entire year-long signal, they discovered a structure hidden within the dataset. The rhythmic knocking, when viewed across its full duration, formed a single continuous frequency modulation trace, one that resembled the decay curve of a resonant system, finally exhausting the last of its stored energy. The system had not been random. It had been releasing energy slowly, methodically, deliberately, until nothing remained. In that final curve, in the last faint pulses before the abyss went completely silent, analysts found a minuscule cluster of frequencies that did not match any known natural process. A cluster arranged in a descending sequence, symmetrical and measured, a pattern indistinguishable from a slow, fading heartbeat. And beneath that, embedded in the last detectable pulse, a faint oscillation nearly identical to the final signal recovered from the breathing capsule years earlier, too faint to decode, too brief to classify, but unmistakably matching in structure. Two phenomena, two trenches, two impossible signals, separated by decades and continents. And both ended the same way, with a final patterned breath from the deep, followed by absolute silence. After the rhythmic knocking faded and the trench returned to apparent quiet long-term monitoring systems, detected an unexpected shift in the oceanic acoustic environment. The silence that replaced the knocking was not uniform, but exhibited a subtle decrease in background noise across multiple frequency bands. The abyss, normally filled with the constant turbulence of microcurrents, sediment falls, and biological activity, now reflected acoustic energy differently. Where once echoes had returned with diffuse scattering shaped by the trench's complex geometry, they now dissolved into the void with unnatural smoothness. Sonar pulses emitted toward the trench penetrated deeper, traveling farther down into the crust before attenuating, as though something beneath the abyss had unlocked a new pathway for sound to travel. This change was first noticed when a low-frequency calibration pulse emitted from a research vessel failed to scatter at expected density boundaries. Instead, the pulse refracted downward, tracing a long arc before fading into a region that previously absorbed sound completely. Attempts to reproduce this behavior confirmed that the trench had become more acoustically transparent. The geological layers that once reflected sound like a labyrinth of rigid structures now behaved like a unified medium, transmitting vibrations with minimal interference. This shift implied that the crustal stress distribution had altered significantly, perhaps influenced by whatever processes drove the rhythmic knocking during the preceding year. Deep mantle tomography surveys conducted shortly afterward revealed another anomaly. Beneath the trench, a column of unusually warm material extended upward from the mantle, forming a thermal plume inconsistent with known tectonic models. Such plumes usually required millions of years to form, but the new thermal gradient had emerged within decades, detectable only because of improvements in global monitoring. The plume did not resemble volcanic upwellings. It lacked the seismic signatures associated with rising magma. Instead, it appeared as a zone of slightly elevated temperature, surrounded by compressed rock, displaying unusual acoustic permeability. This suggested that the rhythmic knocking might have been associated with a deep mantle reorganization event, one that subtly restructured the trench's internal architecture. As researchers analyzed patterns encoded within the year-long knocking sequence, they discovered something even more perplexing. When the entire dataset was visualized spectrotemporally, the knocking's amplitude modulations aligned with patterns resembling interference structures, similar to those generated when two oscillators approach frequency synchronization and then drift apart. These structures suggested that the knocking had responded dynamically to external events, altering its modulation in relation to distant seismic waves, atmospheric pressure shifts, and even seasonal temperature cycles in the ocean's surface layers. The system had behaved not like an isolated oscillator, but like one participating in a global network of interacting geophysical rhythms. This interaction was not passive. During strong seismic events outside the trench, the knocking's amplitude increased slightly, as though absorbing and re-emitting external vibrational energy. During periods of intense oceanographic activity, large storms, shifts in major currents, the rhythm altered subtly, mirroring environmental fluctuations. Such behavior implied a deep feedback mechanism, one that combined geophysical and hydrodynamic inputs into a single oscillatory output. The trench had acted like a global resonator, receiving forces, processing them, and releasing them in a steady rhythmic pattern. The discovery of the thermal plume below the trench prompted further investigation. By analyzing the resonance patterns captured prior to the knocking cessation, researchers were able to reconstruct a rough model of the subsurface structure. Their findings suggested that the knocking originated not from the trench floor but from a region several kilometers below it, inside a stratified zone where mantle rocks were partially molten and saturated with supercritical fluids. These fluids, under enormous pressure, could form pockets of compressible material capable of supporting acoustic oscillations. But natural oscillations lacked the temporal precision observed in the knocking. They drifted, they decayed, they destabilized. The knocking, by contrast, maintained coherence even as its surrounding environment shifted. This led to a hypothesis regarded as fringe at first, but gradually gaining traction. The rhythmic knocking may have been a manifestation of a deep earth resonant structure transitioning between stable states. Certain minerals, under immense pressure and temperature, exhibited quasi-periodic stress-release cycles capable of producing sound. If the mantle plume beneath the trench interacted with these mineral phases, a self-sustaining resonance might have emerged, powered by geothermal gradients and modulated by tectonic forces. Such a system could theoretically maintain long-duration oscillations, but the degree of temporal precision remained unexplained. As investigations deepened, correlations began to emerge between the knocking and other deep ocean anomalies recorded in distant basins. Some of these anomalies dated back decades, even centuries, preserved in old seismic records and misinterpreted as background noise. When reanalyzed with modern acoustic tools, these records revealed rhythmic structures faintly similar to the trench knocking, but weaker and less coherent. These ancient anomalies appeared in patterns that suggested a migration slow, geological, directional. The anomalies moved along subduction zones, across mantle discontinuities, and through interconnected deep crustal conduits, eventually converging on the trench where the modern knocking had been detected. This suggested a long-lived phenomenon, one that migrated through Earth's interior over immense spans of time, drawn toward regions with specific geophysical configurations. The trench, with its unique structure and access to mantle plumes, might have been the final convergence point, where the resonance concentrated enough to become detectable at the surface. The discovery raised a profound question. Had the rhythmic knocking been the culmination of a slow, planet-spanning journey of resonant energy migrating through Earth's interior? If so, the abrupt cessation of the knocking might represent not a failure, but a completion, a release, an exhaustion, or a transformation into a new state. The behavior of the trench after the knocking ended supported this idea. The acoustic transparency, the altered thermal gradient, the unexpected permeability of crustal layers, all indicated a release of stored energy or a reconfiguration of subsurface structures. The trench had not simply returned to normal, it had shifted into a new equilibrium. Further analysis revealed a final, subtle anomaly. During the last day of the knocking, just hours before the final pulse faded into silence, the deepest sensors recorded a single, ultra-low frequency disturbance. This disturbance was so faint that it fell below traditional detection thresholds, but after amplification and filtering, a pattern emerged, a long, drawn-out modulation spanning nearly 20 minutes, containing harmonic structures never recorded before. When visualized, the pattern bore striking similarity to the final resonant imprint found in the resurfaced capsule's last breath, a long decaying curve converging into a single narrow-band oscillation. The match was not exact, but statistical analysis placed the similarity far beyond coincidence. Two independent phenomena separated by decades, thousands of kilometers, different geologies, different environments, had produced nearly identical final decay signatures. This discovery forced researchers to confront a possibility both unnerving and intellectually expansive, perhaps the deep ocean, the mantle beneath it. And the structures formed at the boundaries between them were not isolated systems, but interconnected resonant domains, capable of transmitting patterns across vast distances and timescales. Perhaps what emerged in the resurfaced capsule and what sounded from beneath the abyss were expressions of the same underlying process, a deep earth resonance born of geological dynamics, capable of imprinting itself onto physical structures, sustaining itself across extreme conditions, and eventually dissipating only after releasing its full stored energy. In this interpretation, the rhythmic knocking from below the abyss was not a message, not a signal of intelligence, not the heartbeat of an organism hidden in the deep, but the earth itself, shifting through cycles of resonance, too subtle and slow for human perception, expressing its internal transitions through patterns encoded in rock and water. After the final pulse faded, no further anomalies emerged. The trench returned to its dark stillness, and the mantle plume stabilized into a new equilibrium. Sonar pings once again echoed normally. Instruments recorded nothing beyond natural turbulence. The abyss consumed its secrets, leaving only data patterns, correlations, unanswered questions. The deep returned to silence. But the silence felt different now, charged with the memory of something rhythmic, ancient, and vast that had passed through and moved on. After the final faint echo was recorded, an isolated impulse slipping quietly through the water column before dissolving into background silence, the global monitoring network shifted into a phase of watchful stillness. Though no further rhythmic knocking emerged from beneath the abyss, researchers continued to observe the subtle after effects rippling through the Earth's deep structure. The resonance, though extinguished, had imprinted itself onto geological, hydrological, and acoustic systems across a vast span of the planet. Those imprints, though fading slowly, behaved less like remnants of a localized event and more like diminishing waves from the collapse of a worldwide oscillatory cycle. Long-range seismic networks, originally calibrated to detect major earthquakes, began returning anomalies that existed at the very threshold of detection microdisturbances in the mantle transition zone, occurring at depths where pressure and temperature forced minerals to undergo phase changes. These microquakes were too small to be cataloged as tectonic phenomena, yet they clustered along lines tracing global subduction arcs. Their distribution matched, with surprising precision, the historical route inferred from decades-old faint knocking patterns, rediscovered in archival hydrophone data. It was as though the deep Earth had experienced a prolonged vibrational migration, a resonance wave slowly circulating along the planet's interior boundaries before releasing its final signal at the deepest trench. Oceanographic patterns shifted as well. In regions thousands of kilometers away from the trench, minor anomalies appeared in sound speed profiles. These anomalies manifested as narrow vertical conduits, thin columns of water slightly altered in chemical and thermal characteristics. The columns persisted for weeks, then months, their geometry slowly twisting with the movement of deep currents. At first glance, they resembled weak thermohaline structures, but their density signatures did not match any known water mass. Instead, they behaved as if a portion of the ocean's interior had been subtly reorganized. Thin pathways, where resonance energy once passed, now lingered as faint structural shadows, too weak to serve any functional purpose, yet too coherent to dismiss as random variation. Acoustic mapping of these conduits revealed unusual scattering properties. Sonar pulses that passed through them experienced microscopic delays as though interacting with a lattice of altered molecular organization. The changes were not biological, not chemical, not thermal. They appeared to be a form of acoustic memory, a residual alignment of water molecules shaped by the sustained passage of deep ocean vibrations. Despite water's natural turbulence and constant motion, these filaments of altered acoustic impedance retained their structure far longer than theoretically possible. Their eventual dissolution matched the slow decay curve of the resonance that produced them. The seabed beneath the trench, once the epicenter of the rhythmic knocking, also underwent subtle transformations. High-resolution bathymetric scans revealed micro-warping of sediment layers, not in patterns characteristic of landslides or tectonic shifts, but in long, feathered ridges aligned with the direction of the previous resonance waves. These ridges resembled ripples formed in granular materials when exposed to sustained vibration. The ocean floor had, in effect, registered the rhythms physically, sculpting faint patterns visible only through careful analysis. Though these ridges were shallow, only millimeters in height, they extended across vast areas, forming delicate seismic fingerprints of the abyssal pulse. Mineralogical samples collected near the trench revealed unexpected crystalline formations, elongated structures oriented in near-identical angles. These formations were composed of high-pressure mineral phases, rarely found in shallow samples, their alignment suggesting that they had grown under directional stress fields, possibly shaped by the sustained knocking. Their formation timelines overlapped precisely with the period when the resonance was active. In essence, the deep earth had crystallized in tune with the pulse. Far above these structures, the ocean's surface remained placid, giving no hint of the slow internal realignments unfolding at depth. But even here, subtle anomalies manifested. Satellite gravity measurements revealed tiny fluctuations in geoid height directly above the trench. These variations were minuscule, far too small to affect navigation, but measurable enough to indicate that mass distribution deep below had shifted. The disappearance of the rhythmic knocking had not merely ended a sound, it had concluded a deep geophysical reorganization. Some researchers propose that the absence of further signals indicated that the deep resonance had expended its accumulated energy. In this view, the rhythmic knocking was the planet's mechanism for dissipating internal stresses built over geologic timescales. Once the oscillation reached peak coherence in the trench and released its final pulse, the system fell quiet because the transition had completed. Others argued that the cessation marked the beginning of a dormant interval in a vastly larger rhythmic cycle, one that might repeat long after current monitoring systems ceased to exist. Support for the second hypothesis emerged when researchers revisited geological records. Certain strata extracted from ancient seabeds displayed rhythmic banding patterns impossible to attribute solely to climate cycles or biological activity. Some of these bandings showed spacing intervals consistent with low-frequency oscillations. When scaled by known changes in continental positions, these bandings formed global patterns, suggesting that rhythmic deep Earth events had occurred many times throughout geological history, each leaving subtle but measurable traces in sediment layers. If such cycles existed, they were vastly longer than anything humans had observed. Each one could span centuries or millennia, gathering coherence slowly as mantle convection, subduction, mineral phase boundaries, and ocean density gradients aligned into rare resonant conditions. When these conditions converged, the deep Earth might emit a slow, rhythmic pulse that propagated through rock and water, leaving temporary echoes, acoustic, mechanical, electromagnetic, before collapsing into silence again. From this perspective, the year-long knocking from below the abyss was not an anomaly, but a recurrence, a brief audible phase of a deep geophysical process rarely intersecting with the timescale of human observation. Yet the final and most unsettling discovery came months later, when a deep-diving autonomous probe deployed into a different trench far from the location of the original resonance recorded a faint ultra-low frequency modulation within the crust. The modulation persisted for only a few minutes before vanishing. It bore no resemblance to the rhythmic knocking. Instead, it resembled the faint, decaying signal recorded inside the resurfaced research capsule, the final breath-like oscillation that preceded silence. The location of this new anomaly was thousands of kilometers from the original trench. The geology was different. The mantle structure beneath the region bore no similarities to the deep mantle plume that once supported the resonance, yet the final signature matched closely enough to compel attention. Researchers concluded that the deep structure of the Earth was still adjusting. Internal stress fields, mantle currents, and subsurface phase boundaries continued to shift after the primary resonance collapsed. The tiny echo detected in the second trench represented a late adjustment, like the last settling vibration of a massive object coming to rest after a long oscillation. After that brief anomaly, no further signals appeared. No knocks, no pulses, no resonant structures. Only the natural quiet of the abyss. But the data collected, compressed, and archived across thousands of terabytes revealed something unmistakable: the pattern of the deep Earth oscillation, when plotted across global datasets, formed a continuous arc. It began as faint anomalies decades earlier, migrated slowly across subduction systems, concentrated beneath one trench, produced its audible phase there, released its stored energy, and then dispersed through interconnected mantle pathways until fading entirely. A global resonance, a planetary exhalation, a long cycle reaching closure. The abyss had spoken in rhythm, then fallen silent. The Earth had shifted from one internal state to another. The deep had completed its pulse, and though nothing more could be heard, the world above remained subtly altered by the passing of that hidden heartbeat. Its oceans, its crust, its mantle, each carrying faint traces of the rhythm that once rose from below the abyss. For a long while after the global resonance faded and the deep trenches returned to silence, it seemed as though the Earth had finally settled into a new equilibrium. Yet the absence of sound did not equate to the absence of change. Across the planet, in domains inaccessible to direct observation, faint transformations continued, quiet, minute, but undeniable. These transformations accumulated in deep time scales, manifesting not as discrete events, but as the gradual rewriting of the planet's internal architecture. The first hints emerged not from the oceanic trenches, but from the mid-ocean ridges, vast volcanic seams continually producing new crust. Hydrothermal vents lining these ridges, long studied for their chemical and biological peculiarities, began exhibiting unexpected shifts in their emission signatures. Fluids expelled from vent chimneys contained subtly altered ratios of trace elements, including isotopes usually found far deeper in the mantle. The anomalies were minor but persistent, and they formed a pattern. Vents closest to subduction zones that once hosted faint, historical knocking signatures showed the greatest deviation. It was as though the deep mantle, having undergone a reconfiguration, was releasing remnants of its altered state through the planet's volcanic seams. Temperature probes in these regions recorded unusual cyclic variations. Instead of the typical slow, steady thermal profiles, the vents displayed oscillatory pulses, temperature waves rising and falling over multi-hour intervals. These oscillations resembled the tail end of a dissipating resonance, a fading echo continuing to express itself in heat rather than sound. They were not rhythmic knocking in any audible sense, but the cyclical nature of the thermal pulses suggested continuity. The deep Earth was still unwinding, still reorganizing, still releasing stored energy in subtle forms. In the oceans above these vents, drifting hydrophone arrays captured broadband noise anomalies. These anomalies did not exhibit the clear structure of the rhythmic knocking, but their spectral distribution carried faint imprints of harmonic relationships. Instead of discrete pulses, the arrays recorded long, diffuse bands, broad sheets of sound that fluctuated in intensity with shifting tides and internal waves. Within these broad bands, careful filtering revealed weak modulations whose frequencies corresponded to the lowest order harmonics of the earlier trench resonance. Though too faint to be perceptible without digital amplification, these modulations marked the lingering memory of a deep structure now decaying toward equilibrium. Meanwhile, gravitational satellites orbiting the Earth detected minute changes in geoid height that propagated slowly along tectonic plate boundaries. These changes formed undulating patterns, like waves of mass redistribution moving through the crust. Although countless natural processes can alter the planet's gravity field, ice melt, groundwater shifts, volcanic inflation, the observed patterns followed no known cycle. They moved with a coherence and directionality reminiscent of a migrating oscillation, tracing pathways that mirrored the ancient routes inferred from faint knocking in geological archives. The deepest boreholes on land, drilled into old cratons and stable continental interiors, recorded subtle shifts in pressure at depths thought immune to oceanic or tectonic processes. Instruments placed kilometers deep exhibited fluctuations in pore pressure that matched tidal phase patterns far more closely than expected. These pressure variations synchronized with distant oceanographic anomalies, suggesting that the resonance had established a temporary coherence across the lithosphere. Even though the audible cycle had collapsed, the internal structure of the Earth remained momentarily unified by its lingering effects. In the weeks following the resonance's disappearance, long-range electromagnetic sensors observed faint, ultra-low-frequency disturbances in the ionosphere. These disturbances were too weak to interfere with communication systems and too irregular to form stable global patterns, yet they appeared repeatedly above regions where the deep resonance had once migrated. Some scientists theorized that the resonance's collapse had released a final electromagnetic shock too weak to be considered a geophysical event, but measurable nonetheless when accumulated across days of observation. Oceanic trenches, on the other hand, remained outwardly unchanged. Their darkness concealed whatever subtle reorganizations continued beneath the crust. Bathymetric scans registered nothing beyond the fine, persistent alterations in sediment geometry left behind by the resonance. The seafloor remained still. The water column above sat in its eternal slow drift. But for those who examined the microstructure's carefully, mineral grains, thermal gradients, acoustic impedance fields, faint traces of the resonance's imprint remained embedded like fossilized ripples. One of the most curious phenomena arose at mid-depth layers of the ocean, within the scattered sound channel where acoustic energy often travels long distances. There, in regions far from any trench or ridge, hydrophones detected intermittent pulses of sound that appeared diffuse, directionless, and short-lived. These pulses did not resemble biological calls or mechanical noise. Instead, they manifested as brief increases in the natural hum of the ocean. Their spectral structure aligned weakly with low-order reverberations of the earlier knocking, though in far more attenuated form. It was as if the deep resonance had left behind scattered acoustic echoes trapped in layers of the ocean where sound could drift, reflect, and resurface long after the source had vanished. These echoes, when analyzed collectively across different basins, formed an uncanny pattern. They resembled the final decay of a global resonance system, a system whose oscillations had once synchronized across thousands of kilometers. Though each echo was weak, their simultaneous appearance across multiple monitoring stations suggested a diffuse global phenomenon, a remainder of the Earth's vibrational reorganization. This led to a hypothesis that extended beyond tectonic behavior, that the Earth itself functioned as a complex resonator, sensitive to internal energy states and capable of storing and releasing those states in multi-phase cycles spanning decades or centuries. The rhythmic knocking detected in the trench represented the coherent, surface-detectable phase of such a cycle. But before and after that phase, the system behaved in silent, imperceptible ways, rebalancing itself through slow pressure redistribution, mineral phase shifts, and mantle convection patterns invisible to human senses. Evidence supporting this interpretation increased when researchers discovered another anomaly, this time not in the ocean, but beneath polar ice. Seismic sensors frozen into the Antarctic crust recorded faint vibrations that matched, in frequency and structure, the lowest frequency components of the earlier resonance. These vibrations, though extremely weak, appeared regularly during seasonal shifts in ice mass. The ice sheets acted as amplifiers, converting minute ground vibrations into detectable signals. The source of these vibrations was traced not to glaciers themselves, but to the deep crust beneath them. This suggested that the resonance had propagated across the entire lithosphere, leaving behind faint oscillatory preferences now excited by any stress alteration. In effect, the Earth had learned a rhythm. Even after the primary pulse fell silent, its memory lingered in the planet's deep structure. Over subsequent months, these residual phenomena weakened further. The thermal cycles near hydrothermal vents stabilized. Acoustic conduits dissolved. Gravity anomalies dispersed. The faint mid-depth echoes ceased. The crust beneath Antarctica quieted. The global afterimage of the resonance faded, replaced once more by the chaotic but familiar noise of geological and oceanic processes. One by one, every trace disappeared except for one. Years later, during an unrelated deep ocean expedition in a trench thousands of kilometers from the original site, a single hydrophone recorded an impulse. The impulse was short, extremely faint, almost lost within thermal noise, but it carried a structure, not a rhythm, not a sequence, just a single, solitary knock shaped by the lowest order harmonic the planet once emitted. It appeared once, never repeated, then vanished again into the abyss. An endnote, a closing punctuation, a subtle reminder that something deep within the Earth had shifted once, would shift again, and that all the silence in the world could not erase the memory of a cycle older than humanity's entire history. The abyss returned to stillness. But beneath that stillness, the planet waited quiet, massive, and patient for the next resonance cycle to awaken. In the decades that followed the last faint impulse recorded in the distant trench, the world's oceans continued their slow, indifferent motion. The resonance cycle faded entirely from public attention, leaving only scattered technical papers, archived datasets, and a handful of obscure geological models attempting to reconcile the ephemeral phenomenon with the immense stability of the Earth's interior. The abyss, which had once echoed with a rhythm impossible to categorize, settled back into its ancient equilibrium, cold, dark, and seemingly immutable. But for those who studied the phenomenon in depth, the true legacy of the resonance was not the knocking itself, but the realization that the Earth's most profound transformations could pass almost unnoticed. Visible only as subtle vibrations through stone and fleeting pulses of sound through water. Over time, even the residual anomalies disappeared. Hydrothermal vent chemistry returned to its baseline profiles. The strange vertical acoustic conduits dissolved into turbulence. Gravity field disturbances flattened into standard geoidal irregularities. The deep crust, once subtly trembling beneath polar ice, solidified into its old unmoving rigidity. The ocean's scattered sound channel, once imprinted with faint, drifting echoes of the resonance, resumed its ceaseless catalog of whale calls, passing storms, and distant tectonic groans. None of these familiar signals bore any structural similarity to the great deep rhythm that had once passed through. Yet in the background of global monitoring systems, hidden among terabytes of unrelated noise, one last artifact emerged, a mathematical one, not acoustic. When researchers combined all recorded data from every trench, basin, ridge, borehole, and ionospheric sensor, and compressed the entire resonance timeline into a single unified representation, the pattern revealed a final truth. The deep Earth oscillation had not been chaotic, nor random, nor incidental. It had followed a precise curve, beginning as faint, scattered impulses in multiple deep basins, then converging like tributaries into a single overwhelming pulse beneath the trench, and finally dispersing into global silence. When the entire sequence was accelerated and analyzed as a whole, its form resembled a perfect decaying waveform, an immense planetary sigh, releasing ancient internal tension before settling into stillness. No life form could have produced it, no technology could have sustained it, and no single geological fault could have generated it. It was the mark of a planetary-scale transition, a moment when mantle currents, mineral phases, crustal stresses, and ocean density boundaries aligned just briefly enough to form a coherent resonance, audible for a fraction of a geological instant. After this realization, the scientific community slowly accepted a conclusion. The knocking from below the abyss had been the Earth itself moving from one long-term thermal and mechanical state into another. Not a catastrophe, not a warning, not a message, simply a release of deep energy accumulated across spans of time too immense to measure by human means. With the transition complete, the planet entered a period of extraordinary quiet. Deep mantle plumes stabilized. Subduction zones exhibited lower than average stress accumulation. Even volcanic activity along several ridges entered a prolonged minimal phase. The Earth, having exhaled its hidden resonance, rested. Decades turned to centuries, and though humanity advanced technologically, no further global resonance events were recorded. Occasionally, sensitive equipment detected faint anomalies, momentary pulses of pressure, slight reorientations of mineral lattices, invisible tremors far below seismic thresholds. But none of these bore the harmonic consistency of the Great Cycle. They were merely noise, the natural friction of a living planet. Eventually, even the memory of the event drifted into obscurity. The archived sonar data gathered dust. The research stations that once monitored the trench were decommissioned, and the ocean closed over everything, as it always had. But somewhere in the deepest parts of the Earth, in regions where no instrument could ever reach the internal architecture that once vibrated with a slow, deliberate rhythm, continued its silent existence. The minerals that aligned during the resonance retained microscopic traces of ordering, too faint to influence anything, too deep to be disturbed. The mantle fields that once carried the oscillation settled into their new equilibrium, their currents flowing in patterns shaped long before human civilizations began, and the world moved quietly along its orbital path, indifferent to the past, content with its rebalanced interior. The abyss remained still. The deep mantle returned to rest. The planet remained silent. And though no sound would ever again ascend from beneath the trench in the same form, the Earth had already spoken once, slowly, profoundly, and completely. There was nothing more to say. The resonance had ended. The cycle was closed. The abyss was quiet. Forever. For a long interval after the deep resonance ceased, the absence of anomalous signals became its own kind of data. Oceanographic archives filled with quiet, years of recordings in which the only sounds were familiar, microseisms from distant storms, the groaning shift of ice along polar margins, the crackle of sediment avalanches sliding down continental slopes, the diffuse background murmur of currents brushing across rugged seafloor. Across this vast acoustic record, the former anomaly appeared only as a completed curve, a bounded feature in time, wrapped in layers of annotation and interpretation. The events beneath the trench were catalogued, parameterized, and eventually folded into models as a completed transition. Earth had shifted, resonance had collapsed, and the system, as far as anyone could tell, had reached its new equilibrium. In this framework, the deep ocean returned to its old characterization, complex but fundamentally stable, an environment whose most dramatic changes unfolded slowly enough to blur into continuity. Yet the resonance did not vanish completely from the planet's internal logic. The cycle had been an expression of physical constraints that still existed, though in altered configurations. Minerals that had aligned under the influence of oscillatory stress retained a faint anisotropy, a directional preference in their internal lattices so minor that only carefully controlled experiments could reveal it. Sediment structures in the trench and along the resonance migration pathways preserved subtle textural signatures, grains sorted in patterns that matched no ordinary current or slope process. Some of these structures were reworked, buried, or erased by subsequent geological events. Others remained, low in the stratigraphic column, part of a layer that future observers could misinterpret as the result of more familiar cyclic forcing. If anyone later drilled cores through these layers, they would see patterns thin, repeating bands of slightly altered grain size or mineral composition, but those patterns could be ascribed to climate cycles or orbital variations as easily as to deep Earth resonance. The physical record was ambiguous, as most records are. Above these stable imprints, the biosphere resumed its independent rhythms. Marine organisms that had lived through the resonance and its aftermath carried no direct memory of it, but their distributions had been nudged by subtle temperature shifts, current anomalies, and nutrient redistributions induced by altered mantle flows and vent chemistry. Some deep fauna expanded their ranges slightly as nutrients increased along former resonance paths. Others retracted into refuges as their preferred conditions shifted. Over decades, these changes accumulated into evolutionary pressures, small but non-zero, affecting reproductive success, migration strategies, and even physiological tolerances. No species could be said to have been caused by the resonance, no more than any specific mountain could be said to have been caused by a particular storm. But the resonance had reshaped the boundary conditions within which life adjusted itself, and in that sense it lingered in biological form as well, in gene frequencies, in niche edges, in the detailed structure of webs spun through the deep. Within the human domain, the anomaly's tangible presence eroded differently. Funding cycles turned to other priorities. Sensor arrays were repurposed or decommissioned. The generation of researchers who had first watched the knocking rise and fade retired or passed away. Their successors inherited a stabilized interpretation resonance as global transition and treated it as one more component of Earth's long-term dynamics. The data were clean, the models convergent, the uncertainties bounded. The phenomenon, in other words, was no longer an open question, but a case study. Graduate students encountered it in condensed form, a series of figures showing the build-up, the steady rhythmic phase, the dispersal, and the after-effects. They learned the curve of the resonance, as they learned the thermal history of the mantle or the cycles of glaciation, a once disruptive insight smoothed into a chapter. Yet the signal itself carried a stubborn undeniability that resisted complete assimilation. When reconstructed and played back at accelerated speeds, the deep knocking sounded like a vast, slow instrument, one striking itself once every so many seconds in a rhythm so precise it bordered on hypnotic. The final decay, when sped up further, traced a curve that felt almost organic, a sequence of pulses whose spacing lengthened ever so slightly before ending in a faint, structured oscillation. Those who listened to the full recording properly scaled, filtered, and compressed could not escape the sensation that they were hearing not merely a physical process, but a conclusion. Objectively, there was no intention, no communication, but at the level of auditory perception, the sense of closure was overwhelming. There had been a beginning, a sustained phase, a weakening, and an end. Humans are pattern-recognizing animals. They labeled it without intending to. A heartbeat, a breath, a sigh. Over longer intervals, as technology shifted and archives were reorganized, even this emotional resonance became attenuated. The data set remained, but the habit of listening to it faded. New anomalies arose in other domains, sudden atmospheric waves rippling around the globe, strange phase-locking events in plasma belts, unexpected synchronization in biospheric cycles. Each of these commanded attention in its time. Each generated its own explanatory arc, from surprise through model building to normalization. The deep knocking, being solved to the extent possible, lost its privileged position among mysteries. It was still there, but it no longer defined any frontier. It stood instead as a reminder that frontiers move, that what once confounded understanding can, given enough context, become merely an extreme but natural case of broader principles. Deep beneath the mantle crust boundary, the actual structures that had hosted the resonance continued to deform, assimilate, and convect. The column of slightly altered mantle material beneath the old trench elongated and thinned as flows carried it laterally. Over hundreds of thousands of years, its thermal anomaly dissipated into the surrounding rock. The mineral phases that had been pushed into strained configurations relaxed. The subtle anisotropies aligned with new stress regimes. The once coherent resonant path dissolved into a diffuse contribution to the overall rheology of the deep Earth. At some future time, perhaps under a different arrangement of continents and oceans, another set of conditions might arise that permitted large-scale coherence. But that potential belonged to times so far beyond the horizon of present structures that predicting it in any concrete way was meaningless. The possibility was no more and no less than the generic possibility that the planet's interior would, under certain alignments, continue to explore the full range of behaviors permitted by its physics. In this long perspective, the year-long episode of rhythmic knocking was neither trivial nor central. It was a single excursion in the state space of the Earth, a path taken once, then left behind as conditions changed. Its amplitude and coherence made it stand out against the background of more chaotic activity, just as a storm might stand out in weather records, but it was still governed by the same underlying constraints. The human capacity to detect it, interpret it, and record it was an overlay, a temporary lens. That lens, too, would pass. Eventually, the monitoring networks that had captured the resonance decayed. Sensors failed and were not replaced. Cables severed. Data links shut down. A few stations persisted longer than others, maintained for unrelated purposes: navigation, resource monitoring, communication relays, but their focus shifted away from deep acoustic surveillance. The knowledge that resonance cycles could exist remained embedded in theory, influencing models well after the last direct measurement device had ceased listening. And then, over centuries, even that influence diffused, replaced by refined abstractions that no longer needed explicit historical examples to justify them. Far in the future, long after the array era, other observers, not necessarily human, not necessarily terrestrial, might attempt to reconstruct the history of the planet from what remained: mineral assemblages, isotopic gradients, orbital remnants, field anomalies frozen into rock. They might infer that the Earth had undergone episodic internal transitions, that its mantle had rearranged itself in discrete steps across its lifespan. They might build models of hypothetical resonance cycles, deducing them from static evidence, much as earlier humans deduced ancient climates from ice cores and sediment. They might, in their own way, hear something of what once resounded beneath the abyss, but they would not hear the actual knocks. Those had been a phenomenon of a specific era, recorded by specific instruments, maintained by a specific species, for a specific span of time. To the planet, none of this mattered. The Earth's interior continued its convective churn, carrying heat outward and recycling crust inward. The oceans thickened or thinned, deepened or shallowed, depending on distant contingencies. Continents collided and rifted, mountains rose and eroded, basins opened and closed. Each rearrangement created new possibilities for coherence and resonance, but the vast majority of them remained unexpressed in any way that could be noticed from above. The pulse through the trench had been detectable only because, for a brief overlap of conditions, an internal transition had intersected with a period in which sensors were present and tuned correctly. Remove any element, the resonance, the sensors, the interpretive frameworks, and the event would have passed unremarked. Just one more internal shift among countless others. What remained, finally, was the recognition that even in circumstances where observation is possible, the deepest processes of a world do not arrange themselves for the sake of being known. They unfold according to constraints, histories, and interactions that predate and outlast any observer. The rhythmic knocking from below the abyss was one such unfolding, a process that, from the planet's perspective, simply happened as it must, given the state of the interior at that time. Everything added by listening mystery, meaning, metaphor, was a secondary layer, transient and local. In that sense, the story of the resonance closed long before any narrative about it did. It ended when the last organized pulse departed the trench. when the last structured oscillation dissolved into the unstructured background of tectonic noise. All subsequent reflections, models, and reinterpretations were echoes of that end, reverberating in minds and systems rather than in stone and water. When those, too, eventually ceased, when archives failed, languages shifted, and the chain of interpretation broke, the only memory of the resonance left anywhere would be the minute adjustments it had contributed to the material state of the world. Those adjustments, folded into the immeasurable accumulation of all other adjustments, would have no distinct identity. They would not be separable, even in principle, from everything else the planet had ever done. At that point, the resonance would not merely be silent. It would be indistinguishable from the fabric it had briefly disturbed. And the abyss, whose depths had once transmitted a rhythm precise enough to mimic intention, would again be only what it had always been beneath every story told about it: a volume of cold water above slow, dark stone, moving through its own cycles, without witness, without commentary, and without need of ever being heard again. On timescales that dwarfed the memory of instruments and the span of any single lineage, the resonance episode settled quietly into the larger chronology of the planet. It became one among countless transitions, a small reconfiguration in the thermal and mechanical budget of a cooling world orbiting an aging star. The mantle's convective cells that had once combined to support the coherent oscillation lengthened, sheared, and recombined into new patterns, each pattern rearranging where heat rose, where crust thickened, where basins deepened. The deep ocean adjusted with them, but always indirectly, its density fields and current pathways responding to changes imposed from below and above rather than dictating them. In the stratigraphy of the seafloor, the interval corresponding to the resonance left a layer barely distinguishable from those above and below it. A slightly anomalous assemblage of plankton shells here, a modest variation in trace element ratios there, a thin horizon where sediment grains aligned in ways best explained by sustained vibration rather than by steady currents. Without context, no one looking only at those layers would pick them out as extraordinary. They were a subtle perturbation in a record dominated by more obvious shifts: climate swings, productivity booms and crashes, changes in terrigenous input. The deep Earth cycle that had once translated into a year of perfectly timed knocks registered in the sedimentary archive as a nuance, not a proclamation. In the inner architecture of the crust, however, the episode left a more persistent but equally inscrutable mark. Zones of rock that had passed through the resonance acquired slight differences in crack distribution, in grain boundary orientations, in the alignment of microscopic inclusions. These differences altered how those zones would behave under future stress, when faults later accumulated tectonic load, when magmas intruded, when isostatic adjustments rippled through the lithosphere. In some places, a fault that might have ruptured abruptly instead slipped more slowly. In others, a magma ascent corridor widened a fraction more easily. Each deviation fed forward into subsequent events, not as a dominating cause, but as one factor among many in the tangled feedbacks that shape a planet's evolution. The resonance did not decide any future earthquake or eruption, but its trace was folded into the probabilities that governed them. Far above, the layer of observers that had once monitored the anomaly, those capable of building arrays, running models, and asking questions about the nature of the signal, remained confined to a narrow slice of time, thin enough in the geological record to be almost invisible. Their infrastructure corroded or was subducted, their archives decayed or were overwritten, their conceptual frameworks were succeeded by others or lost outright. The recognition that the deep Earth could pass through coherent oscillatory phases depended on that layer's presence, its tools, and its habits of thought. Once those elements dissipated, the planet's internal dynamics no longer intersected with that particular mode of comprehension. The cycles continued, the interpretations did not. On broader spatial scales, the episode took its place alongside phenomena occurring on other worlds, though no one was there to compare them. Giant planets with fluid interiors supported their own sets of global modes, channeled through metallic hydrogen shells and stratified layers of helium and heavier elements. Rocky bodies with different compositions and cooling histories followed different paths through their own state spaces, some with vigorous convection, others nearly frozen solid. Each had its own repertoire of possible resonances, defined by its size, structure, and thermal state. Most of these oscillations occurred without any interface to external sensing. They came and went as purely internal rearrangements, their only record being the altered distributions of stress and temperature they left behind. In that larger context, the year of rhythmic knocking beneath a single terrestrial trench was not unique. It was one realization of a common principle that sufficiently complex, stratified, energy-bearing systems can, under certain constraints, pass through regimes where coherent oscillations briefly dominate their behavior before yielding to more diffuse dynamics. On Earth, the coincidence of one such regime with the existence of ocean bottom arrays and analytic capacity made it audible. On other planets and moons, comparable transitions occurred in silence, unregistered by anything but the internal variables of the systems themselves. As time pressed outward, the particular details of the resonance blurred even within the planet's internal memory. Mantle parcels that had once participated in the coherent modes were stretched and folded beyond recognition. The specific stress alignments that had given rise to the precise timing of the knocks were replaced by others, each as contingent and transient as the last. Continental configurations changed, ocean basins migrated, new trenches opened while old ones shut down under convergent margins. Each new arrangement brought with it the potential for new patterns of deep oscillation. But whether any of those patterns would resemble the documented episode or be detectable by any future observers remained entirely dependent on coincidences of structure, state, and sensing. From the vantage point of any instant, the deep ocean after the resonance seemed indistinguishable from the deep ocean before it, an environment beyond familiar light, structured by pressure, temperature, and the slow motion of dense water masses. Hydrothermal plumes rose or faded according to local tectonics. Mid-depth sound channels carried noise or remained relatively quiet depending on storm tracks and ice dynamics. Sonar pulses, when they were still used for anything, returned echoes shaped by topography, sediment, and biology, not by hidden global rhythms. To most practical endeavors, the resonance had no bearing. Shipping routes, fisheries, climate patterns, resource exploration all operated on scales and within frameworks that did not need to account for a once-in-an-era deep Earth oscillation. Only in the most abstract treatments of planetary behavior did the episode retain a role. There, it served as an existence proof, a reminder that even apparently stable background systems can harbor long time-scale, large-scale modes that become briefly dominant. It was invoked in discussions of how to interpret incomplete data about other worlds, and in arguments about the necessity of humility when confronting signals whose timescales and amplitudes do not fit familiar categories. Its specifics mattered less than its mere occurrence. Knowing that a planet can breathe in a way that registers as a coherent global signal, even if only once in a great while, changed nothing about the underlying physics but shifted the expectations of those who modeled it. Eventually, as with any example embedded in theory, even that role diminished. New observations, new anomalies, new systems with their own coherent episodes enlarged the catalog. The trench knocking became one point among many in a multi-world library of transitions, and in that larger ensemble, its individuality faded. It remained as a labeled case in a classification tree, a leaf on a branch in a structure that did not depend on any single instance to justify itself. Long after these abstractions had run their course, the conditions that had once sustained the resonance finally receded beyond any possibility of recurrence. Radioactive heat sources decayed, secular cooling thickened the lithosphere, convective vigor declined, the range of accessible internal states narrowed, and with it the diversity of possible global modes. On a sufficiently long horizon, the Earth's deep interior approached a simpler regime: sluggish convection, thicker, more rigid crust, smaller thermal contrasts. In that asymptotic future, the kind of global oscillation that had once imprinted itself through rock and water no longer lay within the system's reach. The planet's capacity for that particular expression was not infinite. It belonged to a phase of its life that eventually passed. By then, there were no arrays listening, no models running, no archives storing waveforms. There was only the world itself, evolving according to the constraints of its composition and history. Whatever had once been recorded, simulated, and debated existed only in the rearranged positions of atoms within rock, water, and whatever else still occupied the surface. The resonance's contribution to that arrangement was inseparable from the contributions of billions of other processes. It had no boundary, no identity, nothing that could be meaningfully distinguished as the part left by the knocking as opposed to everything else. From that perspective, the story closed in the only way such a story can. A complex system passed through a region of its state space where its behavior became unusually simple: a rhythm, a pattern, a set of recurring impulses. For a brief interval, conditions allowed that pattern to be both expressed and perceived. Then the system moved on. The pattern decayed, its energy redistributed into other degrees of freedom. The perception ceased long before the last microscopic consequences did. And eventually, even those consequences merged into the undifferentiated background of all other changes. The abyss remained, not as a place of secrets kept or revelations made, but as a particular arrangement of depth, pressure, and rock within a cooling planetary shell. The resonance remained only as an episode that had once perturbed that arrangement and then disappeared into it. Nothing listened anymore. Nothing needed to. The deep had spoken once in regular pulses that resembled knocking, and once in global vibrations that resembled a breath, and both times the meaning of those sounds existed only in the minds and instruments that heard them. Once those were gone, what remained was exactly what had been there before any detection was possible: a world turning in space, its interior shifting slowly, its oceans moving restlessly above stone. All of it following laws that require no audience and carry no narrative beyond the one briefly imposed by those capable of constructing one. Beyond that brief imposition, there was only the planet and its cycles. And within the deep, beneath any future trench, beneath any ocean that might remain, the same unvoiced fact: whatever rhythms arise there, however regular or strange, will begin, persist, and end entirely on their own, on a time frame long after human presence had dissolved into geological anonymity. The Earth's internal cycles continued to evolve slowly, steadily, without witness. The resonance that once rolled through crust and mantle had been only one episode in a far longer sequence of structural adjustments. With the lithosphere thickening and mantle plumes weakening, the deep interior entered a quieter regime, but not a static one. Residual thermal gradients persisted for millions of years, driving small convective rolls and modest shifts in mineral phases at depth. These changes did not manifest as coherent global rhythms. Instead, they produced localized pockets of stress and relaxation, each too small to coordinate into anything resembling the once detected deep earth knocking. Still, across immense spans of time, even these minor motions contributed to the slow reorganization of Earth's internal structure. As continents drifted further, their configurations introduced new boundary conditions for deep flow. Some edges became locked in prolonged collision zones, thickening the crust and forcing mantle material downward. Other edges thinned gradually, allowing small portions of the asthenosphere to rise. These motions released faint, sporadic tremors, irregular, brief expressions of underlying dynamics. None carried the repeating precision of the resonance event. Most were too diffuse to propagate beyond a few tens of kilometers. They were the natural movements of a planet that still possessed internal heat, not the signature of any emergent coherent mode. Ocean basins, reshaped by these continental motions, deepened or filled in, Trench systems changed geometry as subduction zones migrated. New trenches formed as old ones shut down, not abruptly, but through the slow roll of tectonic drift. Each trench possessed its own acoustic environment, governed by the interplay of water mass density, pressure gradients, and seafloor topography. But none acquired the particular combination of properties that had once allowed a coherent global resonance to manifest audibly. The conditions of that earlier era, a unique alignment of mantle temperature, mineral elasticity, crustal geometry, and oceanic stratification, became unrepeatable with the planet's declining thermal energy and evolving architecture. Still, within each trench, patterns of movement persisted, sediment sliding down steep slopes, lithified layers cracking under strain, hydrothermal fluids rising through permeable pathways. Every so often, these motions generated small acoustic signatures, fleeting clicks, faint rumbles, abrupt fractures. Had any listening array still existed, these sounds would have created dense stochastic data sets typical of a restless crust. But without correlation, without rhythm, without the unmistakable precision that once defined the knocking, they would have held no special significance. They were noise, part of a continuous spectrum of micro-events that accompanied the deep planet's gradual cooling. In the mid-ocean ridges, volcanic activity diminished as mantle temperatures fell further. The production of new crust slowed, altering the chemical balance of hydrothermal vent fields. The superabundant life that once thrived around those vents gradually adapted or retreated as plume temperatures cooled and mineral availability shifted. Over time, entirely new assemblages of organisms evolved unrecognizable to any era that preceded them, but their biological rhythms bore no connection to the ancient deep resonance. Life adapted to local gradients, not global oscillations, and the deep biosphere's pulses expressed metabolic cycles, not mantle-scale coherence. Far above, in the dissipating atmosphere of a planet losing internal heat, surface processes continued their own slow transformations. Weather systems weakened over geological time as tectonic activity subsided and volcanic outgassing declined. Ocean-atmosphere interactions diminished in intensity, reducing storm frequency and altering circulation patterns. But all of these transitions occurred on timescales too gradual to produce sudden shifts, and none carried acoustic signatures that could penetrate to abyssal depths. Despite the profound quiet that now defined the planet's deep structure, certain relics of the resonance episode remained embedded within the physical fabric of the world. In some mineral phases, subtle alignments persisted, microscopic orientations of lattice defects that formed during the era of global oscillation. These alignments had no effect on the planet's macro behavior, but they remained as atomic fossils, silent witnesses to a vanished mode of planetary expression. If one could zoom into the crystalline frameworks of rocks, drawn from the deepest subduction zones, faint patterns of stress alignment might still be inferred, a molecular-level imprint of a once coherent rhythm. In the oceans, traces of ancient acoustic pathways survived in the form of unusual stratification patterns locked into sedimentary sequences. Thin bands of compacted grains, aligned in directions that no local current could have produced, indicated that vibration once played a role in their deposition. Such bands were uniform across vast distances, suggesting a single, planet-scale origin. To any species analyzing them in the distant future, they might resemble varves or climate-driven laminations, unless one noticed their uniform orientation aligned not with paleocurrents, but with the global direction of the resonance wave fronts. Even the planet's magnetic field carried faint, indirect evidence. During the resonance era, the mantle's dynamic reconfiguration subtly affected the heat flow across the core mantle boundary, altering convection patterns in the outer core. These shifts left asymmetries in the magnetic field's long-term evolution, small anomalies in paleomagnetic records. Though indistinguishable from other geomagnetic fluctuations caused by internal dynamo variability, these signatures formed part of a deeper record, an encoded map of how the planet once rearranged itself from within. As millions more years passed, even these faint relics drifted toward oblivion. Subduction recycled crustal material into the mantle, erasing the stress alignments and mixed acoustic imprints from the seafloor. The mantle itself, continually convecting on slow, colossal timescales, diluted any memory of earlier geometric states. The magnetic field reversed many times, overriding the contributions from previous configurations. Nothing lasted except the most abstract truth that once, long ago, the Earth had passed through a state where the deep interior spoke in rhythm. Eventually, as the interior cooled further and plate tectonics slowed toward cessation, the possibility of any future resonance declined to zero. With less heat, less convection, and fewer sharp density contrasts, the planet lost access to the structural configurations necessary for coherent global oscillations. It transitioned into a quiet world, its crust thick and rigid, its mantle sluggish. Oceans shallowed and then evaporated or were trapped beneath new layers of ice, depending on the evolving climate and the luminosity of the aging sunday. Whatever deep acoustic pathways once existed collapsed into immobility, long after even the oceans were gone, leaving behind salt plains or frozen crustal depressions. The regions where trenches once yawned still contain the deep scars of subduction. These relics of a once dynamic planet preserved the geometry of ancient plate boundaries, but no water remained to carry sound, and no monitoring arrays could detect anything even if there were something left to hear. The last vestiges of the resonance had been subducted, recrystallized, mineralized, and erased. Only the rearranged mantle currents, now negligible, carried the faintest memory of an interior that once vibrated in near-perfect synchrony. And yet, in the most remote geological future, as the sun expanded into a subgiant and the Earth's surface grew uninhabitable, some hidden part of the mantle still carried the legacy of that ancient rhythm, not as oscillation, but as structure. The layering of minerals, the frozen arrangements of convective rolls, the subtle differences in phase boundaries, all stood as the final consequence of the cycle. It was no longer a sound, but a shape, a silent architecture expressing what the planet had been. Then the crust cracked under the stresses of thermal expansion. The oceans boiled or froze away entirely, and tectonics halted fully. The mantle stiffened, convection ceased, and the inner architecture solidified forever. No resonance could ever arise again. All cycles of deep vibration, all potential for coherent oscillation, all rhythmic expression vanished completely. The Earth's last internal breath, taken eons before, had long since dissipated. All that remained was a silent, cooling sphere, preserving in its inert rock a faint, untraceable echo of a rhythm that once passed through water, stone, and time, and then was gone. As the planet continued its drift through astronomical time, the silence that followed the deep resonance settled into something more profound than absence. It became the defining state of a world whose active interior had transitioned from dynamic motion to long, slow cooling. The patterns and processes that had once shaped the planet with restless complexity, the convection rolls, thermal plumes, tectonic collisions, subduction-driven recycling had all diminished until they operated at scales so slow, so imperceptible, that even a million years would show only the faintest reshaping of rock. Yet the story of the deep did not end the moment all resonance ceased. A cooling world still changed, only at rates approaching geological stasis. And in these final ages of planetary quiescence, new structures emerged. Structures formed not by internal energy, but by the long reach of external forces acting on a planet that could no longer respond in the ways it once had. Over tens of millions of years, tidal interactions with the moon shifted gradually. As Earth's rotation slowed and the moon drifted farther away, the tidal flexing of the crust weakened. Once, these tides had induced microscopic strains in the lithosphere, providing a delicate but measurable input into the planet's stress fields, a contribution that, in the time of the deep resonance, had subtly shaped the timing of the abyssal knocking. But as the moon's orbit expanded and Earth's spin lengthened, these flexural forces diminished into irrelevance. Without tides, the outer shell became more uniform in its static rigidity. Solar radiation, however, grew stronger. As the sun aged and its core converted more hydrogen to helium, its luminosity increased. Surface temperatures rose slowly at first, then more rapidly. Oceans retreated, concentrating into deeper basins, and finally evaporated entirely as the greenhouse effect amplified. What little water remained became trapped beneath layers of mineral crust or frozen into isolated pockets, in the deep subsurface pockets insulated from solar heat, but also cut off from atmospheric cycling. These changes created new acoustic conditions within the planet, though none involved water. The upper crust, desiccated and fractured, gained an enormous thickness of brittle material, capable of transmitting high-frequency seismic waves with minimal damping. Every minor tectonic adjustment, rare and weak by this time, sent tremors through the crust that traveled farther and cleaner than they had in the planet's younger, more ductile days. Had any sensors existed, they would have detected these faint mechanical murmurs spreading through rock like threads of vibration in a silent web. But no detectors remained. The last of the listening arrays had been lost to time long before. All that existed was the planet itself. Deeper still, the mantle continued cooling until convection ceased. Without convection, heat transferred by conduction alone, a process unimaginably slow on human timescales, but inevitable across eons. As conduction dominated, the temperature gradients that once made density contrasts possible diminished. Minerals that required specific pressure-temperature regimes to maintain metastable phases transitioned into simpler forms. The boundaries between different mantle layers softened. The entire interior began to homogenize into a quiet, slowly cooling mass. This final internal transformation produced no rhythmic signals, no coherent oscillations. Instead, it produced a long, steady settling, a planet-wide exhalation stretched across tens of millions of years. Rock contracted imperceptibly, old fractures widened or sealed, chemical potentials equalized. The last remnant of an active geophysical system faded into equilibrium. At the surface, asteroid and comet impacts occasionally disturbed the crust, carving new basins and scattering ejecta across continents long stripped of atmosphere. Each impact generated seismic waves that penetrated deeply, but without an active mantle to modulate them. The waves passed cleanly until they dissipated. These impacts momentarily woke the interior with sudden bursts of mechanical energy, like stones thrown into a still pond. But the pond was stone now, too rigid, too cold to sustain ripples for long. As the sun swelled into a red subgiant phase, the planet's outer layers heated dramatically. Minerals in the crust expanded, cracked, and recrystallized. Even the deepest trenches, once hosts to the resonance and later to deep-time silence, became nothing more than depressions in an increasingly brittle shell. They no longer acted as conduits for sound or zones of dynamic stress. They became fossil topography, relics of a world that had once been vibrant beneath its oceans. When the sun grew large enough to destabilize the planet's orbit and boil away any remaining volatile compounds, Earth's surface entered a phase of intense metamorphism. Rock melted, then resolidified, then melted again. In these cycles, the last physical evidence of the resonance, the subtle grain alignments, the microscopic acoustic lamination in sediments, the faint stress memory preserved in deep mantle minerals vanished completely. Heat erased what time had not already obscured. Eventually, the sun's expansion engulfed the planet entirely. The crust vaporized. The mantle disintegrated. The core dissolved into ionized metal carried away in solar plasma. Every atom of the planet scattered into the star's atmosphere, redistributed in convective cells, mixed with hydrogen and helium, and carried upward toward regions where light itself was born. Nothing remained of the world that had once harbored oceans, trenches, and deep, resonant cycles. Yet the fate of matter ensured that erasure was not the same as absence. Atoms that once formed the minerals aligned by the ancient resonance would circulate in the solar envelope for millions of years before drifting outward in stellar winds. Tiny grains of silicates, iron, and nickel atomically reorganized but still descended from the deep earth would eventually escape the dying sun altogether, traveling into interstellar space as dust. Some of these grains would join nebulae, some would drift into young star systems, some might compact into new planets. If such a planet possessed oceans, trenches, tectonics, and a molten mantle, then deep within its forming interior, the same universal principles would apply: stratification, convection, mineral phase transitions, stress accumulation in rock. And given enough time, hundreds of millions, perhaps billions of years, its deep interior might again align into a configuration capable of sustaining a coherent resonance. Across interstellar distances, long after the last atoms of Earth had dispersed into drifting clouds of stellar debris, the remnants of the planet's deep interior wandered silently through the galaxy. Most became part of diffuse dust structures, random and unremarkable. But some, by coincidence alone, entered regions of gravitational collapse, where newborn stars ignited at the centers of swirling protoplanetary disks. In these disks, dust clumped into grains, grains into pebbles, pebbles into planetesimals. Through collisions, accretions, and mergers governed by celestial mechanics rather than memory, larger bodies formed. Among the trillions of pieces, a few microscopic grains that once belonged to Earth's interior fused into the building blocks of an entirely new terrestrial planet. This world, like countless others, developed through the standard thermodynamic choreography of hot beginnings and slow cooling. At first, it was molten, a sphere of silicate vapor and metal droplets suspended in turbulent plasma. As its outer layers cooled into a crust, fissures formed where escaping heat fractured the stiffening surface. Below that crust, a mantle churned under the influence of radiogenic decay and the leftover heat of formation. Convection cells formed, density gradients sharpened. Deep layers differentiated into coherent zones possessing distinct mechanical properties. The planet's oceans appeared later, condensing from vapor or delivered by icy bodies. Once formed, these oceans reshaped the crust, carving trenches, building basins, reorganizing heat flow. As tectonic plates drifted, collided, and subducted, the deep mantle underwent changes that mirrored, in broad outline, the universal evolution of all rocky worlds with active geology. Stress fields accumulated, released, and reoriented. Mineral phases transformed under pressure, occasionally locking into geometries capable of supporting long-lived vibrational modes. Eventually, as heat flow stabilized and density contrasts achieved a temporary coherence, the new world entered a phase where the mechanical architecture of its deep interior aligned into a resonance-capable configuration. It began not with knocking, not with rhythmic pulses, but with subtle stress shifts that produced faint, long-period vibrations. These internal oscillations rose through the planet's layers, coupling loosely to its oceans, then settling into patterns determined by the planet's unique geometry. Across hundreds of thousands of years, those patterns grew more regular. Thermal plumes rose and fell in sequences. Subducting slabs flexed with nearly periodic tension. Silicate minerals in transition zones aligned into structures capable of storing mechanical energy. Slowly, very slowly, the planet approached a state where its interior could sustain a coherent oscillatory cycle. And when the moment came, whether millions or billions of years after its birth, the deep beneath this distant world whispered its first organized sound. Not heard, not interpreted, not recorded, just expressed. The oscillation took shape like a long, low chord, resonating through stone and water, shaped purely by physics. It was neither message nor memory. The atoms involved had once vibrated within Earth, but they carried no imprint of that ancient planet. Their identities had been erased in the thermonuclear furnace of a dying star. They did not remember. They could not remember. Yet the structure they now form, this new mantle, this new planet, possessed the same universal potential for coherence that all dynamic worlds share. So when the oscillation emerged, it did so as a natural consequence of internal conditions reaching alignment. The deep resonance lived briefly. Then it dispersed into smaller, chaotic microvibrations. Then it faded entirely as the planet continued its own long journey of cooling and drift. It was a cycle complete unto itself, part of a pattern that spanned worlds without needing to connect them. And that is where the story ends. A resonance arose once inside a world long vanished. It died, dissolved, and left no lasting trace that mattered. Then, elsewhere, another resonance lived and died in its own time. Not a continuation, not an echo, not a legacy. Just the same fundamental physics unfolding under different skies. The deep speaks only in the language of structure and motion, and only for as long as conditions allow. Then, silence returns until the next world forms, cools, fractures, and vibrates. The cycle needs no witness. It never did. And so the last pulse of the old Earth, once lost beneath the abyss, finds its only true permanence not in memory but in the inevitability that somewhere, someday, another world will breathe in stone and ocean and fall silent again.
We upload new videos every single day, so make sure to subscribe and turn on the notification bell so you never miss what's next. If you enjoyed this video, don't forget to leave a like, it really helps the channel grow. Tell us in the comments what you'd like to see next. Your ideas might be in our next upload. Thank you so much for watching and for being part of our community. Stay tuned, stay curious, and we'll see you in the next video.